Diols can be prepared via addition reactions from alkenes. These reactions are review from chapter 9, and we're going to be talking about anti-dihydroxylation and Syn dihydroxylation. Anti-dihydroxylation uses what they generically call RCO3H, which is a peroxy acid. Sometimes you might see MCPBA listed, which is a specific type of peroxy acid called metachloroperoxybenzoic acid. And Syn hydroxylation uses osmium tetroxide. Osmium tetroxide is expensive, and so on large scale, it's common to use a co-oxidant such as NMO and morpholine N-oxide. And this would reoxidize the osmium byproduct of the reaction back to osmium tetroxide so that you only need a catalytic amount of osmium tetroxide. And this reaction takes a specific type of workup, so sometimes you might see sodium bisulfite, which is a reductive workup mentioned in the reagents for this reaction. Okay, let's look at the mechanism of these reactions. If we look at anti-dihydroxylation first, we're going to treat an alkene with a peroxybenzoic acid. Again, I mentioned that MCPBA is a common example of that. So I'll draw the structure of MCPBA out. Again, that stands for metachloroperoxybenzoic acid. I'm going to go ahead and draw in lone pairs on the oxygen atoms. Okay, so an alkene is both nucleophilic and basic, and in this case it will act as a nucleophile. So we will show the alkene doing a nucleophilic attack on one of the oxygens of MCPBA. And the driving force for this will be the breaking of an oxygen-oxygen bond. The alkene will preferentially attack this oxygen because the other oxygen is a better leaving group due to resonance stabilization. So during the attack, we would have loss of a leaving group. I could take these electrons and put them onto oxygen as a lone pair, but instead I can move them over to form a double bond between that carbon and oxygen. Since I can't exceed an octet on the carbonyl carbon, I have to simultaneously have electrons move. So from here I could take these electrons and move them up to the oxygen, or I could just have it take this proton. Then the electrons from the oxygen-hydrogen bond can come back and simultaneously make a bond with the other carbon of the alkene. So all of this is happening simultaneously. This is called a concerted reaction because there are lots of arrow pushing and electron movement happening at the same time. The product of this step, this one step mechanism, is an epoxide. And this epoxide is meso, so it doesn't have an enantiomer. However, both the bonds to oxygen are either both up or both down, sort of equivalent because it's a meso compound. So you could draw either one. And the byproduct of this step would be metachlorobenzoic acid. And that's a solid, so it's a convenient byproduct for the reaction because you can just filter it off. I'll just redraw this bond. And so this is the product of the first step with RCO3H or MCPBA. And the second step utilizes acid. So we need to draw out some hydronium ion. So whenever we use acid as a reagent, typically our organic substrate will become protonated. So the oxygen of the epoxide can pick up a proton. That actually makes the carbons attached to that positively charged oxygen even more electrophilic than they were before. And so if it's very electrophilic, even a weak nucleophile, such as water, can be successful at doing a nucleophilic attack. We can't exceed the octet on that carbon, so we also have loss of a leaving group. This is undergoing an SN2-like process, and so there will be inversion at that carbon stereocenter, which is how we end up with the anti-diol. Initially, though, this oxygen is positively charged, and so we'll need to show a deprotonation before we're finished with the mechanism. Water is the best base in solution, so we will use that to show the final deprotonation step. Resulting in the final product, which is our anti-diol. Now this product is not meso, and so it will be formed as a mixture of enantiomers. So if I draw one product, I can say plus the enantiomer, which would form from water attacking the other carbon and inverting the other carbon of the protonated epoxide. Let's look at the mechanism for Syn dihydroxylation. So for Syn dihydroxylation, we'll just use again cyclohexene as an example substrate. And we're going to use osmium tetroxide as our reagent. Again, on large scale, there may be a co-oxidant, but you don't have to mention that. And with sodium bisulfite workup will provide the Syn diol. And due to an internal plane of symmetry here, this is a meso compound. So let's look at the mechanism. So we'll start with cyclohexene and then draw out osmium tetroxide. Of course, this is making more than 4 bonds, but it's okay on a large atom such as osmium. When we're doing an alkene addition reaction, typically we start our arrows on the alkene, and so it will do a nucleophilic attack on that oxygen. We need to move electrons onto osmium, effectively reducing the osmium. And then simultaneously electrons from this double bond will come back and form a bond with the other carbon of the alkene. Again, this is another concerted reaction with electron movement occurring simultaneously in one step. Because both bonds from carbon to oxygen are formed at the same time, they'll form from the same face of the planar alkene. So both bonds will either be up or down to between the carbon and the oxygen. So initially we get this, what's called a cyclic osmate intermediate. And the step 2 with sodium, aqueous sodium bisulfite, will reduce the osmium oxygen bonds, and we don't go over the mechanism of this step, it's beyond the scope of the class, but that will produce the final product, which is the Syn diol. And remember, because the product is meso, what I drew here with the down-down alcohol is the same as the up-up alcohol that I showed up here.